Is there an edge of the universe? An observable universe is a small portion of the universe in the shape of a ball comprising of the matter that can be observed from the Earth through different means. In simpler words, there is a lot of universe beyond the range we can see. Although we define the observable universe, which is defined at 93 billion light-years, the boundary of the Big Bang, in actual sense there is no limit or boundary in space, and this is just the limit of time. However, the distance is much farther than 13.8 billion years. This is because the universe has continuously expanded since its formation. You must be confused as to how all this stuff is happening. It is not like objects are traveling faster than the speed of light, but actually, the space between these objects is expanding, which causes them to fly away from each other at great speeds. Can we reach the edge of the observable universe? Theoretically, we can reach the edge of the observable universe. But it is possible under extremely rare circumstances. We can only reach the edge if we travel faster than the speed of light. According to most physicists, this is certainly impossible. We can only reach the edge if transcend spacetime, by employing wormholes, which also is impossible. In the beginning, approximately 13.7 billion years ago, our universe came into existence. The primordial light started shooting across the cosmos and spreading throughout the vast universe. Just a few months ago, NASA released some breathtaking photos of the observable universe. Observable universe is a term that is defined by the speed of light. We can see things only which light reflects or emits to us. What is beyond the edge of the universe? The theory of cosmic inflation says that the entire universe is 10 to the power of 23 times the size of the observable universe. This is a huge portion of the universe that we don't know anything about and are certainly missing. The first view says that beyond the edge, the universe might be an infinite expanse of space and may consist of the same cosmos as we see in the observable portion. The Big Crunch, for some reason, space itself, as it expands, it gains speed in its expansion. If it did not, if for every cubic inch of space there were not just a tiny bit of extra expansion energy built into it, then eventually, yes, all of the matter in the universe, not just the black holes, all the stars, all the dark matter, which is way more massive put together than the stars, would eventually draw us down together. It would slow down our expansion, and it would reverse the expansion, and we would fall into something called the Big Crunch. This notion of the Big Crunch, that one day the universe will just stop expanding and smash us all back into a new singularity, has been around for a while. As late as 20-ish years ago, that was a very real possibility. Our observations just weren't solid enough to know how much expansion power space had. But since about 1997, first with the Hubble Space Telescope of nearby galaxies, then followed by measurements of the cosmic microwave background and its geometry, and then followed by cosmological distances measured by exploding stars called Type Ia supernovae, we are now quite certain that space itself has so much power in its expansion that it's driving all the galaxies so far apart it will overwhelm gravity, and within a few billion years, all of those objects will be driven so far apart that there will no longer be any hope of pulling them back together again. Beyond the Hubble volume you won't just find just other solar systems, stars, and other planets, you will find everything if you go far enough. You may find another solar system with Earth identical to ours with the same weather and facilities just as this one, another Hubble volume that is identical to ours. Inside a black hole, another interesting phenomenon is that there are black holes beyond our universe. Our universe may be inside a black hole. They are nothing but stellar objects that came into creation when the stars collapsed under their mass, which forms an incredibly dense singularity. If you go close to the black hole, you will be pulled towards them because its gravitational pull is very extreme. Once you are in the black hole, what lies beyond the horizon of a black hole remains a mystery. There may be a bigger universe outside our universe. Many parallel universes. The popular scientist Stephen Hawking said that there are many universes out there. The most accepted theory in this segment is the string theory, which involves membranes that vibrate in other dimensions. The effects of this vibration helps to understand the observed distribution of matter in our universe. Based on the same theory, many movies on multiverse and books on the same concept like The Hidden Reality by Brian Greene, and Parallel Worlds by Michio Kaku have been made and produced. Nothing has been directly observed to prove the existence of a multiverse, but the theories suggest that they exist. Dark energy and the multiverse dark energy is 3 times more powerful than the gravity of even dark matter. That's what's really driving the motion of the universe today. So, the edges of our universe are not only expanding, but their rate of growth continues to mysteriously expand as well. Another idea that has recently come about, people were trying decades ago as to figure out certain aspects of the geometry of the universe. Another option involves a universe of universes. Some believe that the whole of our universe could exist in a small bubble, in the midst of a vast array of other bubbles. Theorists call this a multiverse. Interestingly, the idea asserts that these universes can come into contact with one another, gravity can flow between these parallel universes, and when they connect, a Big Bang like the one that created our universe may occur. Others will say the universe does have an effective edge, because it was born 13.82 billion years ago in the Big Bang. We can therefore see only those galaxies whose light has taken less than 13.82 billion years to reach us, about 2 trillion. Those galaxies exist in a sphere of space centered on the Earth that we call the Observable Universe. It's actually about 92 billion light-years across as the universe inflated, far faster than the speed of light in its first split second of existence. The Observable Universe is bounded by a cosmic horizon, much like the horizon at sea. Just as we know there's more ocean over the horizon, we know there are more galaxies, possibly an infinite number, beyond the cosmic horizon. Their light simply hasn't had time to reach us yet. In addition, the normal matter in the universe is mostly made of hydrogen and helium, but about 1 to 2% of the normal matter is made of heavier elements from the periodic table, enabling the formation of rocky planets like Earth and complex, even organic, chemistry. While there's lots of variety, some galaxies are actively forming stars, some have active black holes, some haven't formed any new stars for billions of years, etc. The galaxies we see are large, evolved, and clumped together, on average. For the past 11 billion years or so, the universe's evolution has been slowing down. Sure, gravitation continues to collapse structures, but dark energy begins to work against it, coming to dominate the universe's expansion more than 6 billion years ago. New stars continue to form, but the peak of star formation is in our distant past. And supermassive black holes continue to grow, but shone at their brightest earlier on, with a greater fraction of them fainter and inactive today than during these early stages. We take for granted, today, that space is transparent to visible light, but that's only true because it isn't full of light-blocking material, like dust or neutral gas. But at early times, before enough stars had formed, the universe was full of neutral gas, and hadn't become fully ionized by the ultraviolet radiation from these stars. As a result, a lot of the light we see is obscured by these neutral atoms, and it's only once enough stars have formed that the universe becomes fully reionized.